Hello everyone. On this video we will be continuing our dot product studies and looking at the angle between two vectors. Alright, let me make sure this is clear. Alright. Okay, so for this theorem, what if theta is an angle between two non-zero vectors? We'll call that vector A and vector B. Then cosine theta is equal to the dot product of A and B divided by the magnitude of A times the magnitude of B. Or we apply cosine inverse to both sides. Theta is equal to the cosine inverse of the dot product of A and B divided by the magnitude of A times the magnitude of B. Okay. Now also, we use this equation and we multiply both sides by the magnitude of A and magnitude of B, then we'll see that the dot product of A and B is also equal to the magnitude of A times the magnitude of B times cosine of theta. All right. So if we wanted to look at this geometrically, the dot product can be seen geometrically this way. So if we have, let's say this is here and here. This is vector A, and this is vector B. Okay, so you're probably thinking to yourself, oh, before I do that, this is the angle between the two. Some of you may be thinking, isn't this pretty close to just adding them? Not really. Because if you remember, vector A plus vector B is drawn as initial point to terminal point. Okay, this is initial point to initial point. Okay, so if we had, let's say this is vector A. If we added vector B would be right at the terminal point of A. So these two have the same initial point. So this is vector B. So that means A plus B would be right here. Okay, so A plus B is not the same as the dot product of A and B. All right. So what we're going to do now is we are going to prove our theorem that cosine of theta is equal to the dot product of A and B divided by the magnitude of A times the magnitude of B. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and prove this on the next page. Okay, So for our proof, let's say that we have a vector A and we have a vector B. Okay, now just for comparison's sake, if we had vector A and vector B, if we kind of move this one up, then this would be our A plus B. Vector A plus vector B. But if we have, I'll just kind of block that off a little bit, vector A minus vector B, then that's actually equal to vector A plus negative vector B. Okay, so if we have vector A, let's say if we have vector A here, plus negative vector B, so if vector B goes this way, remember, the negative of a vector is the same length but goes the opposite way. So negative vector B would go this way. So A plus negative vector B would actually go this same direction. So this is actually A minus vector B. Okay, because all we did was take this vector and slide it up here. So this is A minus vector B. So really this gives us our vector A minus vector B. That's how we get our little thing there. And connecting our A and B is our theta. Okay, so we are going to use this triangle to prove our theorem. Okay, so starting off, we know that by the law of cosines, we know that c squared is equal to a squared plus b squared minus 2ab cosine theta. Okay, so what if this is your A, this is your B, and this is your C? And of course, theta is theta. Okay, now we're looking at the length of each of those. So that means the magnitude of A theta, not A theta, A vector minus B vector squared, which is our C squared, is equal to the length of magnitude of A vector squared plus the magnitude of B vector squared minus 2 times the magnitude of A vector times the magnitude of B vector times cosine of theta. Okay. Now, we proved that the magnitude of A minus B squared is equal to this, but what will help us out is also that A vector minus B vector squared is just equal to A vector minus B vector and the dot product A vector minus B vector. Okay, just going by the properties. Remember, the magnitude of C vector squared was just C vector, the dot product of C vector and C vector. So it's the same thing here. Okay, so if we use the distribution property, this whole thing can just be distributed to both of those. So we end up with A vector the dot product of A vector minus B vector minus the B vector times the dot product of A vector minus B vector. Okay, so if we use the distributive property again, move that down here, that means it equals the dot product of A vector and A vector minus the dot product of A and B vector minus the dot product of B and A vector, or we could say A and B vector again, since they're commutative, plus the dot product of B vectors. Okay, so that means that that's still our magnitude of A minus B squared. Okay, so that means the magnitude of A minus B vector squared, this, we can actually reduce that to just equal A vector, the magnitude of A vector squared. Okay, if we combine these two, that's minus 2 times the A dot product of A vector and B vector, plus, we look at this one, that's just the magnitude of the B vector squared, according to our properties. Okay, so it helps us out because we know that A vector minus B vector squared, the magnitude of it, is equal to this, but it's also equal to this, which means these two are equal to each other. Okay, so that means the magnitude of A vector, move that up a little bit, there we go, squared, plus the magnitude of B vector squared minus 2 times the magnitude of A vector, magnitude of B vector cosine theta is equal to this here, which is the magnitude of A vector squared minus 2 times the dot product of A and B vector plus the magnitude of B vector squared. Okay, so if we subtract the magnitude of A vector squared, those two cancel out. And if we subtract the magnitude of B vector squared from both sides, those two cancel out. So we are left with negative 2 times the magnitude of A vector and the magnitude of B vector cosine theta equals negative 2 times the dot product of A and B vector. So if we divide both sides by 2, those two would disappear. So we are left with the dot product of A and B. Oh, we start on the left side. So the magnitude of A and the magnitude of vector B cosine theta equals the dot product of A and B. But if we divide the magnitudes on both sides, we end up with cosine, move that up a little, theta equals the dot product of A and B divided by the magnitude of A times the magnitude of B. Okay, so that's our proof. Again, once it's proven, you're free to just go ahead and use it. All right, so if you are still writing, feel free to press pause. But we're going to do one more, have a look at one more thing before we start on our examples. Okay, so this goes back, I want you to remember that two vectors are parallel when they are scalar multiples of each other. they are scalar multiples of each other. Okay, so for example, you have some vector A equals some constant times the B vector. Okay, those two will be parallel. Okay, now two vectors are perpendicular. Okay, which you may see in the book referred to as being orthogonal. When the dot product of the vectors equals 0. All right, so we're going to use that to lead us into kind of describing the geometric direction of these angles. All right, so geometric direction. All right, so I'm just going to create little separation boxes there. All right, now if you remember, cosine of theta fluctuates between -1 and 1. Okay, so we're going to look at different intervals. So what if we have vector A going this way, and vector B attached at the same initial point goes in the opposite direction? Then that means the vector between, not the vector, the angle between vector A and B is 180 degrees, or theta equals pi. Okay, so for theta to equal pi, if you look at your unit circle, that means that cosine of theta will have to equal -1. Okay, so that means your dot product of A and B would have to equal the negative of the magnitude of A and B vectors. Okay, so that's if we have a straight line. What if theta is an acute angle? So theta is an acute angle when the dot product of A and B vector is positive. Okay, so how do we know that? Okay, well, let's look at an example acute angle. Okay, so this is vector A, and this is vector B, and this is our acute angle theta that's less than 90 degrees. So that means theta is between 0 and pi over 2. Okay, so cosine of 0 is 1, and cosine of pi over 2 is 0. That means cosine of theta is between 0 and 1. Okay, so when cosine of theta is between 0 and 1, you have an acute angle. Okay, what about a right angle? Theta is a right angle when our dot product is equal to 0, just like we showed there. Okay, why is that? Well, let's take a look at our vector A and vector B. Oh, clean that up a little. at a right angle. Okay, so we know that theta is equal to pi over 2 for a right angle. And we know that cosine of pi over 2 is equal to 0. And that can only happen if our dot product is equal to 0. All right. So what if theta is obtuse? So theta is an obtuse angle when the dot product of the a and b vector is less than 0. Okay, why is that? Because we have a sample obtuse angle, which is larger than 90 degrees, but less than 180. We have our a vector, we have our b vector, and we have our obtuse theta. Okay, so that means that theta is between pi over 2 and pi. So we have pi over 2 is less than theta. Get that a little more space, is less than pi. Bring that down a little bit. Okay, so cosine of pi is -1, and cosine of pi over 2 is 0. So that means cosine of theta is between -1 and 0. Okay, now if they're in the same direction, so if you have your a vector and the b vector is really just a multiple of the a vector, so it's the same length plus some. So this whole thing here is your b vector. That means that theta is equal to 0. Or in other words, cosine of theta is equal to 1. All right. Okay, so that's it for the explanation. So let's go ahead and get to a few examples. So if you are still writing, feel free to press pause, but we're going to go ahead and get started on the next page. All right, so let's say, for example, if we let a vector equal points 3, -1, 2, the b vector equal -4, 0, 2, the c vector equal the points 1, -1, -2, and the d vector equal the points 2, 0, -1. And clean that up a little bit. Okay, so what I want you to do is find the angle between each pair of vectors and we want that in radians, not degrees this time, so in radians. Okay, so for problem A, we want to find the angle between vectors A and B. Problem B, we want to find the angle between A and C. And for problem C, we want to find the angle between B and D, vectors B and D. All right, so starting off with problem A, which is vectors A and vectors B, we know that cosine of theta equals the dot product of A and B divided by the magnitude of A times the magnitude of B. Okay, so remember this is A1, A2, A3, B1, B2, and B3. So that's going to equal the dot product of A and B is the first component of A times the first component of B plus the second component of A times the second component of B plus the third component of A times the third component of B divided by the magnitude of A vector. So that's the square root of the first component squared plus the second component squared plus the third component squared times the magnitude of B, which is the first component of B squared plus the second component squared plus the third component squared. All right, so we're going to go ahead and plug those in. So we know that, move that over a little. Cosine of theta is equal to the first component, so you have 3 times -4 plus multiplying the second component, -1 times 0 plus the third component, which is 2 times 2, all over the magnitude of A. So you have the square root of 3 squared, which is 9, plus -1 squared, which is 1, plus 2 squared, which is 4, times the magnitude of B, which is -4 squared, which is 16, 0 squared, which is 0, plus 2 squared, which is 4. Okay, so we end up with -12 plus 0 plus 4 over the square root of 14 times the square root of 20. Okay, so if we keep on calculating, we see we have -8 over square root of 280, which simplifies to be -4 over square root of 70. Okay, so we know that cosine of theta equals -4 over square root of 70. Okay, now a quick little side note. Let's move that up a little bit. Oops. There we go. I'll draw this over here. In this case, your cosine theta is negative, so it's less than 0. So cosine of theta is less than 0, so we know it's going to be obtuse. Okay, so that means we apply cosine inverse to both sides. So that theta equals cosine inverse of -4 over square root of 70. So you plug that into your calculator, and you should get 2.069 radians. Remember to have your calculator set to radians and not to degrees. If you have it set to degrees, you'll get a different answer. All right. So let's start on problem B. And separate that a little bit. Okay, so for problem B, we have vector A and C. Okay, so we know that cosine of theta is going to equal the dot product of vector A and C. We kind of separate that a little. Divided by, that's a little longer than I need, the magnitude of the A vector times the magnitude of the C vector. Okay, so that's going to equal the first component of A times the first component of C plus the second component of A times the second component of C plus the third component of A times the third component of C all over the magnitude of the A vector, the first component squared plus the second component squared plus the third component squared times the magnitude of the C vector, the first component squared plus second component squared plus third component squared. Little error there. There we go. Okay, so now we can go ahead and just plug those in because we know that A, you have A1, A2, and A3, and C1, C2, and C3. Okay, so those are your components. So we're going to go ahead and plug those in. Okay, so cosine of theta is equal to 3 times 1 plus -1 times -1 plus 2 times -2 for your A1, C1, A2, C2, and A3, C3 divided by, now we find the magnitude of those vectors. So the magnitude, well, the magnitude of A, we actually did that one up here, but still 9 plus 1 plus 4 times the magnitude of your C vector. Bring that down a little. Okay, so you see that C, 1 squared is 1, -1 squared is 1, and -2 squared is 4. There we go. Bring that back up. Okay, please excuse the glare as the sun moves. So does the glares. Okay, so that's going to equal 3 plus 1 minus 4 over square root of 14 times the square root of 16. Honestly, we don't even have to worry about the denominator because 3 plus 1 is 4. 4 minus 4 is 0. So you have 0 over the square root of 14 times the square root of 16. Okay, so we know that cosine of theta is equal to 0. Okay, so we know that, little side note, cosine of theta equals 0 means it's a right angle. So when cosine of theta is equal to 0 and it's a right, we know it's a right angle, so that means that theta has to equal pi over 2. All right, so we're going to continue problem C on the next page. So if you are still writing, feel free to press pause, but we're going to do problem C on the next page. Okay, so continue, and because we're on a different page, I'll write our B vector is -4, 0, 2, and our C, oh, not C vector, D vector equals 2, 0, -1. Okay. Actually, what I want you to do is, I want you to go ahead and press pause and find the angle of between B and D vector on your own. All right, so assuming you've pressed pause and you've already worked it out, let's verify your answer. Okay, so we have cosine of theta equals the dot product of B and D vector all over the magnitude of B times the D vector. Okay, so that's going to equal, multiply the first component. So you have -4 times 2. Multiply the second component, which is 0 times 0. Multiply the third component, which is 2 times -1. all over the magnitude of the b vector. So that's negative 4 squared, which is 16, plus 0 squared, which is 0, plus 2 squared, which is 4, times the magnitude of the d vector. 2 squared is 4, 0 squared is 0, and negative 1 squared is 1. Okay, so hopefully you are on the right track. So that means that cosine of theta is equal to negative 8 minus 2 is negative 10. All over, you have square root of 20 times square root of 5. Okay, so you can actually combine those two. So you have negative 10 over square root of 100. 20 times 5 is 100. Put them all under the same square root. Okay, so that means that cosine of theta equal to negative 10 over 10, or cosine of theta equals negative 1. Okay, so we know for cosine of theta equals negative 1, that means that theta has to equal 5. Or you could apply cosine inverse to both sides, completely up to you. Okay, now quick note, I don't know if some of you noticed this or not, but vector B and vector D are parallel since they're scalar multiples of each other. So that just means that vector B is actually equal to negative 2 times vector D. Okay, so if you multiply vector D times negative 2 times 2 is 4. Negative 2 times 0 is 0, and negative 2 times negative 1 is 2. Okay, so it's actually parallel. All right. So hopefully this video made sense, and I will see you on the next video.